In this situation, an object was kept on top of a plank, let us say, or a table, and this object is slowly, slightly toppling down. Okay, so this object was kept over here, and this object is slowly toppling down. Alright, so we will have to analyze what is the angle covered, and we have to write down energy equations and force dynamical equations for the same. So let me draw the vertical line from which it starts to topple. So this is the initial position of the center. This is the center, let us say, of the object, and this happens to be the radius. Alright, so when this object turns by an angle theta, then now the center happens to be situated over here. The force of gravity is in the downward direction as usual along this axis, along the y-axis, and let us say if this angle is the angle theta via which it has rotated, then this angle also happens to be theta. If we try to think about what are the forces that are acting on this particular object with a circular cross section, it can be a sphere, solid cylinder, hollow cylinder, disc, anything. So if we try to analyze the forces that are acting on this object, let us say a sphere for example, then we will see that there is a normal reaction force that is acting away from this point of contact. So there is this normal reaction force that acts away from this point of contact. Let me draw it like so. So this is the normal reaction force. And then there is the force of gravity which acts in the downward direction, the usual regular force of gravity that acts from the center. This object is a uniform object, so the center of mass is also the center of gravity, and the gravitational field is also uniform, and the gravitational force is going to act through the geometrical center of the object, which happens to be the center of gravity as well. So here the force of gravity is going to have two components. One component is going to be towards this point of contact, and one component is going to be perpendicular to the point of contact. We ignore the perpendicular component. We would like to understand what happens of the component that is towards the point of contact. So mg cos theta is the component of gravity that is towards the point of contact, minus n, the normal reaction, is the component of gravity that is away from the point of contact. Now this is what does this expression represent? It represents the net force that is acting towards the point of contact, the net resultant force of gravity and normal reaction. This expression represents the net force acting towards the point of contact. Now if we just think about what is happening with this object as it is falling down. So initially the object was kept at this location, and with a instantaneously zero velocity it started toppling, meaning it just began its toppling motion. So the center of mass of the object, if you see, is following this arc. Now this arc is also an arc of a circle whose center is at this point of contact or the critical point. So I am talking about this particular arc. The center is following this particular arc, and this happens to be the center of the circle of which this arc is a part. Now because of this situation, we can say that the center of mass of this object is actually undergoing circular motion instantaneously. So let us say this point is the point which is the center of the circle around which the center of mass is instantaneously undergoing circular motion. So now mg cos theta minus n represents the net force towards the center, and this happens to be the centripetal force. Now this is going to give us mv squared divided by r. So centripetal force happens to be mv squared by r. That is the reason why. Alright. The second analysis that can be done on this particular object is the analysis of how much energy it has lost while falling. So for that, we need to understand how much height has decreased as the object is falling. So let's do that analysis. Earlier, the center of mass was at this location and this was the radius. Now the center of mass is at this location, and we have seen that this angle is theta. This also is the radius. So if I complete this triangle, then in this triangle, what do I get? I get this to be r, this to be theta. So this much part is r cos theta. Adjacent side to the angle theta happens to be r cos theta. Now the height dropped by center of mass is this height. This is the height dropped by center of mass. So this is the total radius r. From this point to this point is the total radius r. Let us say from this point till this point is the radius r. Now the height dropped by center of mass is nothing but r minus r cos theta. This is very easy to understand. So loss of potential energy is going to be mg r minus r cos theta. So this is going to be loss of potential energy. Alright, so this loss of potential energy by energy conservation, we can simply say that this is going to be equal to the gain in kinetic energy. Now comes the interesting part, how to calculate the kinetic energy in this particular question. Here is where most of the students and individuals are committing errors. So here the kinetic energy of this object, okay, can be calculated in basically two distinct ways, and it is important not to combine the two ways. So the center of mass is currently moving with a velocity v. So there will be kinetic energy associated with center of mass, that will be half m vcm, which is the velocity of center of mass square. This also happens to be the velocity of center of mass only. Okay, so this is the translational kinetic energy. Okay, now at the same time we need to realize that this object is rotating as well about the center of mass, because without rotating it wouldn't turn. It has to rotate in order to turn. This has to be understood from one's own physical intuition and physical understanding of the situation. So it is turning, let's say, with omega velocity. This point of contact is stationary. So the point of this point P's velocity will be v minus r omega in the backward direction, or rather v minus r omega in the forward direction, r omega minus v in the backward direction. But all of it does not matter because this point is stationary. That's why v minus r omega is equal to 0. If we are talking about point P, for the point P, v minus r omega is 0, therefore v is going to be equal to r omega simply. Therefore omega is going to be equal to v divided by r. This is a simple understanding that we should have. Okay, now about the center of mass, let us say this object has a moment of inertia I. So plus I into half, which is half I omega square. So this is I about center of mass, omega about center of mass. Now this is one way of writing down kinetic energy, and like you can solve these two equations to get the unknowns that are required. Usually what is asked is what is the angle theta the object has to cover in order for the normal reaction to become 0. This is what is usually asked. So if we put normal reaction 0, then we understand that we get theta as an unknown and v as an unknown. Omega is known in terms of v basically. So v and theta are the unknowns, and we can eliminate conceptually the velocity v in order to find out theta. So let us try to continue the analysis and do that. So let us say this is equation 1 and this is equation 2. So when does the object lose contact? It loses contact when this normal reaction becomes 0. So by just putting normal reaction 0 and using these two equations, that is the last moment where these equations are still valid, because once the normal reaction becomes 0, then the equations completely change, because now there is like as the object is falling down, it does not it's just following as the object is falling down, the center of the object will just follow projectile motion, and the object will keep rotating at a constant angular velocity with which it was rotating basically. So the angular velocity will not necessarily increase, and only the translational kinetic energy of the object will increase after the object is falling. So the equations of dynamics and energy will change when we are talking about the object having left the point of contact. So after the object has left the point P, then the equations are different. So when we put normal reaction 0, we are literally using these equations as the last instant, at the last instant of time when these equations are still valid. Alright. So let me simplify these two equations. So let us say, what do we get on simplifying? Here omega, we have to write down this omega as v by r, as already discussed over here in this explanation, and we basically need to eliminate v. So for that, what we can simply do is, from this equation we can understand that mv square, because mv square is going to appear over here multiple times, so mv square is going to be equal to rmg cos theta. So let us say, here how do I make mv square appear? So what I'll do is, instead of moment of inertia, I'll write m k square. So this is why we use the radius of gyration. We do not know the moment of inertia as, let us say, it is 2 by 5 mr square or 1/2 mr square, etc., because we haven't specified the object. I said that it is a sphere, but it could be anything basically. So let us derive the formula in the most general sense. So mk square, where k is the radius of gyration, this happens to be the moment of inertia. Now here m will come, and in place of omega square, v square by r square will come. So this last term I can replace with, let's say, let me rewrite this thing, half m vcm square, okay, plus half mk square vcm square upon r square. So now I get mv square in all the terms. See, in the first equation as well as the second equation, I have got mv square involved, and here also mv square is there. So what I can simply do is, I can substitute mv square to be equal to rmg cos theta by taking r towards this side. Now if I do that and simplify, what do I get? I get mg r 1 minus cos theta is equal to half rmg cos theta plus half k square upon r square. Instead of mv square, we are going to write rmg cos theta. rmg cos theta. Alright. So here we can clearly see that now Rmg will get cancelled from the entire equation because Rmg is not 0, and towards the left hand side we will be left with 1 minus cos theta is equal to cos theta by 2 plus k square upon 2r square cos theta. Alright, so since we have to find out cos theta, it is best to isolate all the terms having cos theta and then simplify. So that means we can write this equation as 1 is equal to cos theta into bracket 1 plus half k square over r square. Alright, which implies 1 is equal to cos theta by 2 into 3 plus k square upon r square. Alright, after simplifying this, and so this is 3 by 2, I have taken 2 out of the parentheses and will be left with 3 plus k square upon r square. Alright, so if required we can take the LCM over here, or we could keep the formula as is. Basically I prefer keeping the formula as is for ease of remembrance. So this will imply that our cos theta is equal to 2 upon 3 plus k square upon r square. So this is the easiest to remember basically. Now let me box this particular formula. So this is the angle theta at which the object will leave the upper surface and start its free fall essentially. So this is the angle at which the normal reaction will become 0. An important remark in this particular example is the fact that instead of writing this energy expression as half mv square plus half I omega square, we could have written down this energy equation in one step, or rather this energy expression in one step, if we would have analyzed the energy about the point P. Why? Because the point P happens to be the point about which this object is instantaneously performing pure rotation. So whenever we have a point or an axis about which an object is performing instantaneously pure rotation, then that axis is called as the instantaneous axis of rotation, or the point would be called as the instantaneous point of rotation. So this requires some imagination that about the point P no translatory motion is happening, only rotational motion is happening about the point P. All the particles in the body are performing purely rotational motion. A common confusion that happens is, okay, center of mass is also translating. Yes, no problem is there with that. Center of mass is translating, just like in normal rotational motion. Let us say if the body is rotating, then all the points in the body are also translating, meaning moving with some velocity v. But that phenomena that a particle is moving with a velocity v is not exactly called as translation. Translation means that all the particles are moving with the velocity of the center of mass. That means the translation of the object is happening vis-a-vis the velocity of the center of mass. Here all the particles are not moving as the center of mass is moving, parallelly to the center of mass basically. So the trajectory of the entire body is not according to the trajectory of the center of mass. Here it would be most accurate and correct to say that the entire body is undergoing pure rotational motion about the point P. Let me draw a few arcs for making students understand this. Let us say these are the arcs about the point P around which the particles are moving. Alright, so these arcs are circular arcs centered at the point P. That is why pure rotation is happening about the point P, which can be said to be the instantaneous point of rotation. An axis passing through P that is perpendicular to the plane of the paper or the plane of the board, let us say, is going to be considered as the instantaneous axis of rotation. Now, about the point P, we could write down the kinetic energy simply as half I about the point P and omega about the point P square. Now omega about the point P is the same as omega about center of mass by this very logic. This logic still persists and remains because the point P is instantaneously stationary. So V minus R omega is going to be 0 and omega about point P. So basically here we can say that, let us say, if this is omega about point P, then the velocity of the center V is going to be given as R omega simply. So this relation about the point P still persists. Alright, so omega about the point P is simply going to be omega about center of mass. So I'll just replace that with just an omega. Now here IP is to be found out using parallel axis theorem. So we can write down this to be equal to half IP is nothing but ICM plus MR square into omega square. Now if we do analyze this properly, then we are getting back the original expression of energy. So energy is the same only, even if it is calculated about the point P or calculated vis-a-vis the center of mass. So we'll get half ICM omega square plus half mr square omega square, half m r square omega square, but r square omega square can be replaced with v square because of this expression, v being equal to r omega. So this is an important remark wherein we can find out the energy via finding out the energy about the instantaneous point of rotation or the instantaneous axis of rotation as well, not only about the center of mass. In some questions, it might be easier to write down the energy with respect to the instantaneous point of rotation or the instantaneous axis of rotation rather than trying to find it out with respect to center of mass. So we should be aware about this particular technique as well.